Okay, welcome everyone to this presentation on Slither. So the goal of this presentation is going to give you some insight into how we use Slither internally, how you can extend it, and how you can use some of the hidden capability and feature of the tool. This talk is going to be a bit dense in some aspect, it's going to be a bit low level. My goal is really by the end of this presentation, you have a bit more insight into how you can leverage all the kind of hidden capability of Slither. First thing first, my name is Josselin Feist. I'm the engineering director of the blockchain team at Trail of Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We are not a blockchain company, but we have been working in the blockchain space for like 7 years now. We do a lot of traditional application security, cryptography, machine learning. One thing that I think differs us from a lot of our competitors is that we spend a lot of time doing research, writing academic paper, writing blog posts, and building open source tools such as Slither, Medusa, and so on. But yeah, as I mentioned today, my goal is going to focus on Slither, and my goal is going to help you to understand some of the things that you will be able to do using the tool. If you don't know Slither, it's a static analyzer for Solidity and Viper. We have been building Slither for like 6 or 7 years now. It's open source, it's in Python. Most of the people, like 95% of people that are using Slither from the command line. They are using Slither to find vulnerability, you run Slither on your code base, and there is like a bunch of inbuilt detector. But actually Slither comes with a lot of additional features such as printer and a full Python API. On a really high level, how does it work? So Slither starts by taking the compilation artifact from the compiler, Solc or Viper. It takes the IST that is provided by the compiler. It recovers a couple of information from that, create a control flow graph, translate the source language into its own intermediate representation, perform a bunch of analysis, and provide all of that to the different usage from vulnerability detections to like a Python API. If you're familiar with compiler, the architecture is really similar to a compiler outside of the code generation. So it's basically a compiler without code generation. As I mentioned, I think the main use case and where Slither is known is for its inbuilt detector. So Slither comes with 19 plus public detector ranging from optimization to high-level vulnerabilities. We have been building this detector for like many years now. They are using our audit. We have found many vulnerabilities using Slither through our audit or bug bounty. You can find a couple of examples here, and you can find some of the examples of detector on the left side. A couple of quick command line flags that you might know or might be useful. If you want Slither list detector, print the list of detector. If you want Slither on the target, detect detector name, you are just going to run one detector. Pretty straightforward. Now, once you run Slither on a code base and all the detector, you might have false positive, you might have false alarm. So some of the findings are not going to be real finding, and actually most of them are not going to be real finding. This is kind of pretty standard with static analysis. So the process that you are going to have to do is to triage the result. To do that, you can apply a couple of techniques. The first one is that you can add comments to the source code to disable some detector. Pretty straightforward, pretty standard in any static analyzer or linter. So you can use disable next line to disable the next line, or you can disable a block of code. I have an example in a few slides. Similarly, some detector comes with custom code commands to help the static analyzer, in particular for the reentrancy. I'm going to give an example, it will make a bit more sense. But just to give you like the example of the code commands, here you have a function. You start by saying Slither disable start, the name of the detector. You close with the same command but disable end. Basically, if you do that, any reentrancy found by Slither within like these two kind of commands are going to be not shown to the user. This is just a way for developer to iteratively disable some of the false positive. As I mentioned, some detector comes with custom information that you can provide as code command. Here in this example, you have a variable, and you can comment with custom security non-reentrant. This will indicate to Slither that this variable, any call to this variable, is non-reentrant. For example, if you have a code base where one variable is a contract, and this contract is controlled by the owner, and if the owner is malicious, you can have a reentrancy. As a developer or as a security researcher, you might have a trust assumption that you trust this external call, you trust this contract, you don't want reentrancy based on that. So here you can enhance kind of like the result of Slither by adding these comments. This is really like an effective way to disable many false positives that stem because the static analyzer cannot know that you are trusting this variable. You have also a couple of additional ways to triage results. We have an interactive triage mode where you just run triage mode. Every finding is going to be asked, tool is going to ask the user if every finding is a true or false positive, and is going to create a database for that you can reuse, so that you do a triage once from your command line, create the database, and every time you run, you don't have to do the same triage. If you are a developer, we also recommend to use our GitHub action, Slither action. This is going to be connected to GitHub, and then it's going to use a code scanning feature from GitHub. It's really kind of a nice user interface to triage a different result. Something that might be confusing when you start playing with Slither on arbitrary code base is what you should provide as a target. So you run Slither and the target. Most of the time, what we recommend is to rely on the underlying compilation framework. Foundry, Ardat, whatever you want to use, where the target is basically the root directory of your project. The reason for that is that, as I mentioned at the beginning, Slither is going to rely on the compiler information. So we need to be able to compile the code. If you run Slither on a file directly, if you run Slither file.sol, you need to be able to compile this file. And as you might know, from the moment you have complex code base with remapping, it's a bit tricky. You have to provide a lot of flag for the remapping. SALC is not the best friendly remapping compiler. That said, we have a couple of additional support. For example, for Foundry, we are going to ask Foundry to give us a remapping information, so you can run Foundry on the Foundry code base. You can run Slither on the file directly, and Foundry is going to do the magic for us. TLDR, run it on the root directory unless it's a Foundry project. Something that I think not everyone know about it is that we can do on-chain analysis. From the moment the code is provided on Etherscan on any Etherscan-like platform, Slither will do everything automatically. So if you do Slither 0x like the address, Slither is going to query Etherscan, retrieve the source code, do the compilation, and provide you like with the result. And this works with probably most of the testnet and like a lot of different EVM-based layer 1, layer 2. You know, we support Optimism, Arbitrum, and so on. So basically, with no additional setup, with no additional kind of configuration, you can run Slither on anything which is live and verified. Okay, before I go into the additional feature, is there any question regarding the detector or anything I've presented so far? Okay. We have a notion of printer in Slither, which is basically any way for us to provide visual representation of the code base. We use printer a lot during audit to get quickly information about a different code base. Here there is an example of an inheritance graph. As you might know, when you review like a Solidity code base, developers tend to overuse inheritance, and you can quickly get to a point where you have like 5 or 6 levels of inheritance. And sometimes it's just difficult to kind of represent, you know, for yourself where are the different functions, where are the different variables, where everything is coming from. So to help, you know, ourselves during audit, we have built like a lot of so-called printer to do this type of thing. So we have like a inheritance graph, contract summary, and a couple of additional ones that are a bit more complex. Similar idea, if you want Slither, list printer, list of printer, target prints a printer name, you are going to use a specific printer. Usually the printer are either going to provide a graph representation of something, or it's going to be a text-based visualization. We're also working to integrate all of that into VS Code to make it a bit more easier, but it's a work in progress. Okay, so here is where I wanted to go. Slither provides a full Python API that is going to allow you to extend its capability. It's going to allow you to create custom script. It's going to allow you to create like custom tools. Over the years, we have built a lot of specific and dedicated tools on top of Slither. All of them are open source. To give you some examples, Slither check upgradability. This is a specific tool that is going to try to find misuse or issue related to the delegate call-based proxy. For example, if you have a proxy, if you have a version 1 implementation, a version 2 implementation, you have to be careful with the order of the variable. You have to be careful with the function shadowing. You have to be careful with all these type of things. Slither can do it automatically, can check for that automatically. Slither check ERC, kind of the same idea. If you are building an ERC, a contract that is supposed to follow an ERC, it's not that difficult to make a mistake, an incorrect parameter type, like you are missing a function or things like that. Slither check ERC is going to do the conformance check for yourself. Another tool which is really cool if you are building kind of bot or if you are building kind of on-chain analysis is Slither read storage. So if you take an arbitrary code and you are trying to find what's the value on-chain of a specific variable, it can be tricky because you have to compute the storage slot of a specific variable. If you do it for an array or for a mapping, you have to do like the proper calculation. Slither can do it just for you. You just need to connect to an RPC node, and Slither with storage will give you like the information. All of that is built thanks to its Python API. So we have built Slither in a way that it's extensible, in a way that you can use it as a library and do everything I just mentioned yourself. To give you a quick introduction. So here in this code, we are creating a Slither object, pretty straightforward. From Slither, import Slither, and yeah, this is not working. And here you just instantiate a Slither object, and this is a target. As I mentioned previously, as a target, you can also provide an address. So here I'm doing the same. I'm creating a Slither object, and this is the address of USDT. If you are doing this in a bot, if you are trying to run it, in a way that you're going to query a lot of different on-chain contracts, you can provide an API key. This exists for Etherscan and for all the different platforms that are supported. This is just because otherwise you are going to have a rate limit with Etherscan, and it's going to allow you to make more queries per second. From the moment you have the Slither object in Python, there are different layers. There are different kind of group of information. And on a high level, you can consider 5 layers that we are going to go through one by one. The first one is compilation unit, then contract, function, control flow graph, and expression and intermediate representation. TLDR, it's really from like the high level to like the lower level, one by one. Compilation unit. If you are not familiar with compiler, this might be a bit kind of unexpected, but a compilation unit is basically a group of files used in a single call to the compiler, Salsi or Viper. Most of the time, in most of the code base, you are going to have only one compilation unit, but that's not always true. Depending on the compilation framework and depending on the setup, you might have more of them. For example, Hardhat might do like partial compilation when you change one file, and instead of compiling everything, it's going to compile like a subset of file. If in Foundry you use multiple Solidity version, like you compile with 0.7 and 0.8, you are going to have multiple calls to the compiler. The way you can access them is that from the moment you have the Slither object, you have an array in compilation units. Why this matter? Some of the API in Slither might be a bit confusing if you don't consider this notion of compilation unit. For example, if you look for a contract, if you have multiple compilation units, you can have the same contract in multiple compilation units. If you are just trying to create a prototype, if you are just trying to hack quickly on top of it, you can just take the first element of the array and you don't care. You have to consider this a bit more if you are trying to build something which is a bit more robust, something which is going to work with any arbitrary code base. So depending on where you are at and what you are trying to build, you can discard everything I've said or not. From the compilation unit object, you can access to the contract, which is straightforward. You can access to the contract derive. This is an important kind of differentiation. The contract derive are basically in the inheritance tree, the leaf, like the contracts that are not inherited by any other contract. When you are going to analyze a code base, maybe you care about like the intermediate contract, maybe you don't care. Like for example, ERC20 is frequently like inherited by like other contract. Maybe you want to go through it, maybe not, it depends on what you want to do. We have other helper like get contract from name, pretty straightforward. You can access all the top-level objects being objects that are not defined within a contract, like structure, enum, event, variable, function, but not the ones that are within the contract, the ones that are at the compilation unit level. To give you an example, so in all the example I'm going to give, the first line are going to be always the same. Basically, you load USDT and you take the first compilation unit, and the rest is going to be different in the following example. Here what we do is that for USDT, we print all the contract, and then we print all the contract derived, just to see kind of like the difference between both. If you run that on USDT, like this is a list of all the contracts that are within the source code of USDT, and here are all the derived contract. As you can see, for example, you have ERC20 basic, ERC20 in the contract USDT, but if you look at which one are like the most derived, they don't appear because they are inherited by the Tether token. From compilation unit, you can go into contract. So similar idea. On the contract object, you have a lot of helper, you have a lot of things that are going to help you to navigate the properties. So the name of the contract, straightforward, the inheritance. Here you can follow the inheritance in both directions, so you can know what are the contracts that inherit from the one you are manipulating, or what are the contracts that are inheriting from it, so both direction. And it follows the T3 linearization order, if you're familiar with that. You have all the objects that are related to the contract, enum, event, structure, and so on, access to the function, access to the state variable. And similar for state variable, if you care about the order, you have a specific helper for that, otherwise you have the list of accessible variable. Here is also where you have to be a bit careful, because for example, state variable order are going to be all the variable following the order. Accessible are going to be the variable accessible by this contract. The difference rely on private variable. If you have a private variable in contract A and you inherit the contract in B, B is not going to have access to the private variable of contract A. So here it's an example where you have to be a bit careful into what you are doing depending on what you are trying to achieve. An example, so again, first three lines are the same as before. Here what we do, so we load USDT, we take the contract called Tether token, and we print all the state variable. And here are all the state variable of USDT, nothing fancy here. So compilation unit, contract, and if you go one level deeper, you have function. Similar idea, you have a lot of method and a lot of analysis that you can rely on. Solidity signature, the signature version within Solidity. Entry point might make a bit more sense once we're going to go to the control flow graph, but entry point is basically the first node in the function. So if you have a graph, it's like the entry point of the graph. You have access to all the different elements, expression, variable, modifier, and so on. Then you have a bunch of helper that are usually pretty useful when you build script or when you build like any analysis, which are going to be related to help you identify what variable are read or written, and both for state or local. So you have the combination of all of them, like all the state variables that are read or the local variable that are read, and so on. This is at the function level. You have also helper to do it with a recursive lookup in the sense that it's going to follow the internal call. If you analyze a function, maybe you only care about like the state variable that are written within this function. Maybe you care about the state variables that are written within this function, including all the internal call. Depending on what you are trying to do, depending on what you are trying to build, you can use the proper function. Same example as before, we load USDT, and here we are going to print all the state variables that are read by the total supply function. So we load the total supply function, and we just print state variable read. Pretty straightforward. Now we are going to see a bit more of the difference between the recursive lookup and the normal lookup. So if instead of looking at the total supply function, let's say we look at the transfer function. So we load the transfer function. Here we print all the state variables that are read by the transfer function. And here we print all the state variables that are read by the transfer function and its internal call. And here it's going to be different. The reason for that is that if you look at the transfer function of USDT, you have a modifier call and you have a super.call. So like this function has internal call, and here with the API you can decide if you want or not to include them. Does that make sense? Do you have any question? Okay. Compilation unit, contract, function. Now we can go into the control flow graph. So the control flow graph, it's a common kind of code representation in static analysis. Basically, the idea is that you represent your source code as a graph where every operation is a node and the edge of the graph are the control flow. If then else, loop, and things like that. So if you take like this function, it's just like an if then else, it will look like this. It's a pretty common representation in any compiler or any static analyzer. Now, if you are building an analysis that depends on the control flow graph, you have basically two categories. Either you are trying to iterate over all the nodes, like for example, if you want to know if there is a specific operation in the function, you can just iterate over all the nodes. It's a list. You don't care about the order, you just want to know if there is a specific instance. If you are building something which is a bit more complex and you need to respect and to follow the order of declaration of the node, then you need to work through the node. And here you can use this type of pattern, which is like a visitor pattern, where you take a node, you do whatever you want to do as a type of analysis, and you iterate over all the edges that are going out of the node. This is pretty standard in traditional static analysis, but if you are not familiar with building like data flow dependency or this type of things, it might be a bit confusing at first. From the moment you work through a graph in static analysis, you have to be careful on how to stop. You can either iterate only once, or you can iterate multiple times. And this is because you are going to have loop once you iterate from the control flow graph, and because you have loop, if you don't stop the kind of work through the node, it's just going to be an infinite loop. So either you iterate only once, if it's what matters for you, or you can bound the iteration by how many times you want to bound. Or if you are building something which is more advanced and more complex, you need to create a so-called fixed point. So you need to create kind of like a function or like a logic to say I'm going to iterate until I reach some specific valuation or some specific state. Usually, if you start playing with Slither, this is not going to be important. You don't need to necessarily understand that. But from the moment you want to build complex data flow analysis or complex complex kind of analysis, you have to be careful with that. If you build a loop iteration, a control flow graph kind of exploration, and you don't consider this type of things, you are going to have infinite loop. So be careful. Okay. Compilation unit, contract, function, node. Now we go into the intermediate representation. An intermediate representation usually is meant for code analysis. So you have high-level language, Solidity, Viper, Go, Rust, and so on. But a compiler or static analyzer usually don't work on this type of language because they are meant for human. Usually we build intermediate representation that are kind of designed to make the code analysis simpler. Intermediate representation are not necessarily meant to be read by human. They are not the most user-friendly things. You are not going to write within your intermediate representation, but they are really useful once you want to build automated analysis. The most common intermediate representation that you might have heard of is LLVM from the traditional software industry. Our intermediate representation, which can convert from Solidity and Viper, is, I think, pretty straightforward and pretty simple. It has less than 40-ish instructions. It's a linear intermediate representation in the sense that we don't have a jump-up code. We rely on the control flow graph provided by Slither. If you are familiar with compiler, it's basically an hybrid intermediate representation. It's flat in the sense that we don't have nested instruction. Again, if you are familiar with compiler, it's kind of close to a 3-code address, but not exactly, because sometimes we have more opcode. If everything I just said doesn't make sense, it's totally fine. You will see some example. We do a couple of code transformation, code simplification. For example, in Solidity, you have a ternary operator. We convert that into an if then else. Again, our goal is to make simpler to build analysis. And if you have multiple expressions that are exactly the same thing, if then else or ternary operator, it's easier to have one representation for building analysis. So a couple of examples, binary or unary operation, left value, which is assignments, and a couple of opcode. Here is where you can see it kind of looks like a 3-code address. Index for array. We have member for structure. We have a couple of new operators for every time you create a new things. You can see, for example, we have a new structure operator, which is not explicit in Solidity, but we have made it explicit just because, again, it makes easier to build analysis on top of it. Just an example, it's a dereference twice and a subtraction. It will create 3 opcode. This is where you can see we don't have nested operation because in Solidity, like this is nested, you have multiple operations that are going on here. Here it's one by one. Just it makes easier building analysis. On a high level, we have a hierarchy for operation and for intermediate representation. This is just a subset. It doesn't show everything. But just to give you an insight, operation is like the top level class we are using. Every operation is an operation. You can have condition, operation with left value, and call. Operation with left value is basically any operation that does an assignment. So any operation that is equal something, binary, unary, and so on. Then we have things like high-level call, which is basically a call to an external contract, which is both a call and an operation with L value, because when you do an external call, it's both a call and an assignment. Okay, an example of the intermediate representation usage. So here it's kind of like everything we just saw previously. We open USDT, we retrieve the contract, we retrieve the total supply function, and here we just iterate over all the intermediate representation, and we look if there is a high-level call. So we look if in this function there is like an external call to something else. And yeah, there is a call to something else. Because operation have this inheritance and there is like this hierarchy of operation and of type, you can use isInstance to know if a specific operation has a specific type. Every operation object is going to have its set of method, its set of parameter, but yeah, I won't go into all of them. We have additional features and additional kind of parameter that are a bit more advanced and are going to be useful only if you really go like deep and you do like a deep dive into static analysis. But something which is really powerful, we have inbuilt data dependency. Basically, data dependency is going to allow you to know if a variable is dependent from another one. So like, you know, if you have variable B and variable A, is there any value kind of dependency between both? This works at the function level and the contract level. We have a second intermediate representation, which is on a SSA form. It's a traditional form static analysis. We do alias analysis on storage reference. So if you have a storage pointer, Slither is going to try to recover what are all the destinations that this storage pointer can point to. Again, only if you are trying to analyze complex code base. Hopefully, not a lot of people use storage pointer. Okay, where to start? We have securecontract.com, where we have a bunch of tutorial and a bunch of description and exercise. Within the code base of Slither, there is a tool demo project, which is going to help you to kind of get started with like all the wrapper and all the like default configuration. I would recommend to read our detector API. So the code base is a bit large now, but at least if you go and you just focus on the detector, you will see the usage of the API, you will see different pattern of static analysis that is going to help you to get up to speed. Okay, to conclude, yeah, Slither is our static analyzer for Viper and Solidity. We have been building it for many years. It's as mature as it can with respect to the time we have spent on it. If you want to learn more, go on securecontract.com. If you have questions, if you want to explore some idea, it's open source, so feel free to open a GitHub issue, feel free to open a GitHub discussion, join our Slack, and if you want to ping me on Twitter or Telegram, it's just Montili. Okay, thank you for your attention. And